All right. I tried making a video of this, and it only got through 3 problems before it froze on me. So I'm thinking a little outside of the box, taping one camera to another camera, and trying to see if this will work. Hopefully, it won't freeze up on me. But um, as you can tell from the first 3 examples, we're going to look at the integral of dx over x, which is form-fitting to help us identify that the result of this is going to be the natural log of x plus c. Same thing with du over u. It's going to be the natural log of u plus c. So if we use u substitution, still expect the same end result if you get du over u. So here we just pulled out a scalar of 10, and we recognize that it's the integral of dx over x, which is just going to be natural log of x plus c. Here, this has a derivative of 1, so we're going to be able to notice or hopefully recognize eventually that if what we're letting u, which is by itself in the denominator, if that has a derivative of 1, then it's really just going to be natural log of whatever that u is plus c. But here it's not just that, because this has a derivative of -3. So if we multiply both sides by -1/3, it'll allow us to look at -1/3 integral of du over u, which is the integral, or is the result, results in -1/3 natural log of u plus c, and then we just plug in our x because we are on an indefinite integral here. So let's continue this pattern. We see that we have an x cubed here and an x squared, another identifier that we're going to let u be the denominator here. So u, let's move this over so you can see. U equals 5 minus x cubed, which would make du equal to -3x squared dx. But I don't want to replace -3x squared dx. I want to replace x squared dx. So I'm going to multiply both sides by -1/3 again. So this ends up becoming -1/3 integral of du over u. And so it's pretty much the same setup as the problem above. Okay. This is going to be -1/3 natural log of u, which is just 5 minus x cubed. So if you want to skip this step that's in between and just plug in what your u is, feel free to do that. Okay. Next example, we're going to let, we have a higher degree in the denominator here than the top. So we're going to let u equal the entire denominator, x cubed minus 3x squared. Take the derivative of that. You get 3x squared minus 6x dx. And if you notice and you try and compare this to the numerator, you'll realize that, oh yeah, that's just a scalar of that. So in this example, if I multiply by a +1/3, then I can rewrite this as 1/3 integral of du over u, which would make this 1/3 natural log. What is u? U was the x cubed minus 3x squared plus c. Okay. Identify for the next one. When I see this, I see a square root in the denominator. Right away, I know this has nothing to do with natural log as it stands. Remember, this u is to the first in the denominator, and all these and this x is to the first. So this is like a -1 exponent. This is a -1/2 exponent. So you got to be careful. Don't just be a robot doing this homework. We're going to let u equal the 9 minus x squared, which would make du equal -2x dx. And I want to replace x dx, so I'm going to multiply both sides by -1/2. So right now I get -1/2 integral of du over square root of u, or u to the -1/2 du. And this is not a natural log problem. This is just a u substitution problem. So we add 1, which would make it 1/2, divide by the new. So this is going to be -1 square root of u, which was 9 minus x squared plus c. And you can write that a couple of different ways. Looking at this, I think they're just trying to be kind of tricky on the way that it looks. I'm going to let u equal the entire denominator, x cubed plus 3x squared minus 4. And then du equals 3x squared plus 6x dx. If I were to multiply this out, I get x squared plus 2x. So if I multiply both sides by 1/3 here, I can replace all of this with 1/3 du. And that's what I'm going to do. Got a lot of 1/3s here. Negative 1/3, 1/3. Interesting. So we get 1/3 integral of du over u, which is just going to be 1/3 natural log of what our u is, x cubed plus 3x squared minus 4 plus c. Okay. This one, okay, remember, whatever you let u equal, you got to be able to compensate with the du somehow. So, looking at this, I can easily recognize, oh yeah, this is an innermost function. This was replacing something raised to the 2 powers. So this replaces that base. So we're going to let u equal natural log of x, which would make du equal to dx over x. And so this part right here is going to be replaced with the du. And then this is going to be u squared. So this ends up becoming the integral of u squared du. Again, for this example, very similar to this example up here, this is not a natural log anymore, okay, because it's u squared, so it's really just going to be the power rule. Add 1, divide by the new, so you get u cubed over 3 plus c, but what is u? It's the natural log of x, so this is end up natural log of x cubed all over 3 plus c. Okay. Solve the differential equation. This will really show itself what we mean by that in chapter 6 when we deal with separation of variables. And so let me just get into that a little bit for you. If we go back to differentials, we could, if we wanted to, move this up to the top if we multiply both sides by dx, or have that idea if we were magicians and we could. So those will cancel out. So we'll be left with dy equals 3 over 2 minus x dx. And so if we were to integrate both sides here, which right now you'd be like, we've never done that. Well, we're going to do it in chapter 6 quite a bit. This is going to be y plus c, but again, we're going to have the indefinite integral representation for these c's on the right-hand side. We're going to let u equal the 2 minus x, which would make du negative dx. So we multiply, we want to replace 3 dx, so I multiply both sides by negative 3. So then this is going to be y equals negative 3 integral du over u. So if I move it up here, I'm going to get y equals negative 3 natural log of u plus c. And what was u again? U was 2 minus x. So this is y equals negative 3 natural log of 2 minus x plus c. But here's the deal. It says solve the differential equation. It tells us it goes through the coordinate 1, 0. So I got to go find this c value right here by plugging in 1 and 0. Well, if I get 0 here equal to negative 3 natural log of 2 minus 1, which is 1, plus c, well, guess what? Negative 3 times 0 is 0, so c is 0. So at the end of the day, this is going to be y equals negative 3 natural log of 2 minus x. Okay. Hopefully that makes sense. Let's just double check here. Yeah. Okay. So let's go down here to find the definite integral. Okay, we've got a similar setup. We got to figure out what we're going to let u equal. And so I'm going to let u equal the innermost function, the 1 plus natural log of x. I'm going to let that equal u, which would mean du equals dx over x. So if we were to set this up, we're going to get the integral of, well, this is u squared, and then this is going to be du. So this is u squared du But remember, with definite integrals and u substitution, we got to replace our boundaries. So if I plug in 1, this is going to be u of 1 equals 1 plus natural log of 1. Well, that's just 1 plus 0, so this equals 1. U of e equals 1 plus natural log of e. Well, this is going to be equal to 1 plus 1, which is equal to 2. So now I have this new setup. I don't care about this anymore. This is what I'm looking at. Okay, so this is going to be equal to u cubed over 3 from 1 to 2. So that'll be 8 thirds minus 1/3, which is 7 thirds. Feel free to check it on your calculator in case I made a mistake. All right, over here, same kind of idea. There really isn't an innermost function. So our thought process needs to be, well, if I let u equal this, what is the derivative going to be? Well, I see this as the same as 1 over natural log of x times dx over x. I mean, it's the same setup, just written differently. So I'm going to let u equal ln of x, which would make du equal to dx over x. So when I set this up, I'm going to get, all right, this is going to be du, and this is going to be u. So I really have the integral of du over u. I just need to replace my boundaries with values that are in terms of u, as the lights go out here. All right. And so I get this integral. This is natural log of e down here, which is 1. And then if I do the natural log of e squared, that 2 will come out in front. So this is going to be 2 times 1, which is just 2. So this is going to be 2. So really it's similar to the previous problem, except this is going to be natural log of u. So natural log of u from 1 to 2. So this will be natural log of 2 minus natural log of 1. That goes away because if the value is 0, so this is just going to be natural log of 2. Cool. All right. Where's my next page here? So we got some trig integrals that we'll finish this up with. Okay. And hopefully what you'll realize, these should be u substitutions, but I'm going to show you how to do it by just looking at it. You got to be able to compensate for this 1/3, which is going to be multiplied by 3. So I'm going to show you the u substitution one time, and then I'm going to just do it in my head. So if u equals theta over 3, then du equals 1/3 d theta. But I don't want to replace 1/3 d theta. I just want to replace d theta. So then I would multiply both sides by 3. So how do we compensate for that theta divided by 3? We got to multiply our integral by 3. And then this will be the integral of cotangent u du. So then this just comes down to, do you remember what the integral of cotangent u is from today? Well, this is why we learned today, because it is one of our new integrals. This is going to be 3 natural log of sine u. Well, what was u? It was theta over 3. And then that'll be plus 3, or plus c. Okay. So if I'm multiplying by 5 in here, I got to compensate for a 1/5 out in front. That'll compensate for that 5. And so then this will be 1/5 integral of tan u du, which would equal 1/5. And today we actually worked this one out. It's going to be a negative natural log of cosine of u, which in this case was 5 theta plus c. Okay. So if u is 2x, du is going to be 2dx, but multiply both sides by 1/2. So in reality, I might be able to just skip this step right here and think to myself, what's the antiderivative cosecant? Well, that's going to be negative natural log cosecant u plus cotangent u plus c. So this is going to be negative 1/2 natural log of cosecant of 2x plus cotangent of 2x plus c. Okay. Secant, we're dividing by 2, so to compensate for that, that would be like 2 integral. I'll not skip this step. I'll keep this step so you know what we're looking at, okay? Hopefully it doesn't confuse you too much, but again, whatever you're comfortable with, just do what you're comfortable with. So this will be secant u du. So then we just ask ourselves, well, what's the antiderivative of secant u? Natural log secant u plus tan u plus c. So this is going to be 2 natural log of secant of x divided by 2 plus tan of x divided by 2 plus c. Move it over there. Okay. Over here, we can split this up into 2 integrals if you want. So you could look at this as cosine of 3 theta d theta minus the integral of d theta. Okay. So then this is going to be compensating for that 3. This is going to be 1/3 integral of cosine u du, but antiderivative cosine is just sine. So this is just going to be 1/3 sine of 3 theta minus theta plus c, because the antiderivative of d theta is theta. Over here, same kind of setup. You could separate this and make it 2 d theta minus the integral of tan of theta divided by 4 d theta. So when I do that, this is just going to be 2 theta. This right here is going to be, well, the antiderivative of tan is that natural log of cosine u, but it's negative natural log cosine u. So this negative will eventually be a positive for natural log of cosine theta over 4 plus c. Here, okay, for me, I'm still going to look at this and say, you know what? I see this being the u and this being the derivative, because the derivative of sine is cosine. So if we let, u equal 1 plus sine t, du equals cosine t dt. So this will actually end up becoming the integral of du over u, which is what we've worked with today. So this will be the natural log of what u is, which is the 1 plus sine t plus c. Okay, looking at the next problem, let's see, a couple of ideas potentially. We could let, part of it is recognition. Some of you might think, well, do I have to convert this to make this like 1 over sine squared and then simplify the cotangent to cosine over sine and all that stuff? In reality, no, you don't have to do that. To me, you can recognize that the derivative of cotangent is negative cosecant squared. So if I let u equal cotangent of t, then du equals negative cosecant squared t dt. So I'd multiply both sides by -1. So then this would become -1 integral of du over u. So then that would make that negative natural log of cotangent t plus c. Okay. Same thing with this down here. This is going to be u. Derivative of secant x is secant x tan x dx. So I'm going to look at this and think, oh yeah, this is really just du over u. Okay, you can do the sidebar here. U equals secant x minus 1. Du is, secant x tan x dx. So then this just becomes natural log of u, which is the secant x minus 1 plus c. And the last example on the page is really just setting up and splitting it up into 2. In both of these instances, you can say, hey, u equals 2x. So then du equals 2 dx, which would make us want to multiply both sides by 1/2. So both of these are getting a 1/2. So really it just comes down to, do you remember the integral of secant and the integral of tan? And those are from today, so you might have to check your cheat sheet. So there's going to be 1/2, and the integral of secant is going to be your natural log of secant u, which is 2x here, plus tan u, which is 2x. And then it'd be plus c if it was a single antiderivative, but I got that tan part. So then this is going to be the antiderivative of tan is negative natural log cosine. So this would be minus 1/2 natural log of cosine u, which was 2x plus c. Okay. So hopefully that helps. Feel free